Hello, everyone. Hello, Thorfinn. Hello, Lei. Nice seeing you. As always, I suggest to wait another 1 or 2 minutes and then to allow other people to join, and then we'll start. Okay, I think let's begin. So today is the third lecture by Thorfinn, and it will be gently given by Thorfinn and Lei from University of Copenhagen. So Thorfinn, yeah, welcome.
Yes, okay, super, okay. Thanks for the introduction. So let me start by sharing my screen. So Vladimir, I don't think I can share my screen.
Just a second, sorry. Yes, now you should be able to do that.
Okay. Also, make sure that Lei can also share his screen later on.
Sure.
Yeah. Good. Okay. So I'll continue where I left off last week about alignment. I'll do a short recap, and then so hopefully people can understand how fantastic this Burroughs-Wheeler transform is that I'll talk about. And then after this, then Lei Xiao, postdoc that I share together with Rasmus Nielsen from UC Berkeley, he will talk about the uncertainty of sequencing data. And this is presentation that was used in a course at here at the University of Copenhagen. I think it's a fantastic presentation because it really covers all the uncertainty aspects that's associated with high throughput sequencing data. So I also promised Lei that I would not talk too long, so he have plenty of time to go through his stuff. So I'll start and I'll speed it up a bit. Okay. So can everybody see this?
Yes.
Yes. Can you also see my mouse?
Yes.
Yes. Okay. Good. So I'll start with the recap here. So we are focused on the high throughput sequencing data, also called the next generation sequencing data. Not so much third generation sequencing data, but next generation sequencing data. And here we can obtain genomes for whole populations, for entire individuals, and it's something that has been used a lot in the last 10 years. With this platform, you get millions of reads, and all these reads can be understood as short sequences that are sampled with replacement from the chromosomes. And these are normally relatively short, around, if it's ancient, it's around 30 base pairs. If it's modern, it's much longer. It can be around 250 within the next generation sequencing data. That's one of the defining characteristics with the third generation sequencing data, is that you can have 100 of kilobases long reads. So these reads are sample replacement from the chromosome, so we need to figure out where they belong relative to a reference genome. So we take all these reads and then glue them onto a reference genome, so we have their position. If you're working with human, we would of course align this to the human genome. We call this reference-based alignment. And to conceptualize it a bit, we also did some numbers here. So if we have 100 million reads, and these reads are around 75 to 150 base pairs long, then we align those to the human genome and assume that it's an exact match that we are doing. Then we could just do a linear search throughout the genome. It's a 3 gigabase long file. So each of these queries will take 6 seconds. So if you wanted to do this with 100 millions, it would take 20 years. So this is, even in this context, it's not doable. We are also involved with the metagenomic studies where we are using much larger reference genomes. Here it's not a single organism, but it can be hundreds of different organisms, and there the reference genome has a size of 1.5 terabytes. So, and it's impossible to do basic naive search through these large files. So last time I talked about the naive approach for aligning. We have a text, this could be our reference genome, and then we have a pattern, this could be our sequencing data, and then we seek the offsets within our text where we have a match. In this example, we are looking for the AABA, in this long text string called AABAAC and so forth. We find a shift at position 0, at position 9, and at position 12. Again, this is exact match. So the way we do this is that we just shift through everything, entire sequence. So we have n minus m plus 1 shift we need to do before we tip over. And then we do need to do a comparison, which is m comparisons for each shift. This is very slow, and there are approaches for making this better. I went through those last time. That's the Rabin-Karp approach and the Knut-Morris-Pratt approach. This is exact matching, and this will of course work if you really trust your sequences. In practice, there's high uncertainty. They will talk about this associated with high throughput sequencing. So we need to do inexact matching, and this is where I talked about the Swift-Waterman approach. And here you're building a complete matrix that has the dimension of the length of your reference genome and your pattern. So that is also unrealistic to apply in practice. So this is the naive approach that we are doing. This is done for protein sequences also. So before we move on, a short reminder in case you forgot this from the last time. We have a string, this is a sequence of characters. We have a substring, which is a continuous sequence of characters from within the string. Right? If you look at the string called banana, a substring could be the A and A. A prefix is a substring that starts from the beginning. A suffix is a substring that starts from the end of your read. We also talk about an alphabet. In the banana example, we are only observe B, A's, and N, so A, B, N. If you're doing DNA sequencing, then we have A, C, G, and T. So we have an alphabet size of 4. In practice, when we are doing alignment or working with high throughput sequencing data, sometimes we also observe an N. And this N is means that the sequencing machine does not trust the observation it has made. So rather than giving a very, very high probability of error, it just sets it to N. Okay. Also, when you're working with high throughput sequencing data, sometimes you also have small characters and big capital characters. It's the same nucleotide. This is mainly to which strands we are sequencing. It could also be if you have a reference genome, then it could also identify regions which are repeat regions. So sometimes you also get small letters and capital letters. If you're working in a protein alphabet, then we have 20 different proteins. Okay, so this is a short reminder. I also talked a bit about the suffixes. If you look at the banana example, we can list all the different suffixes. We have, it has a length of 6, so we have 6 different suffixes. We can start from the end. It's A, it's NA, it's ANA, it's NANA, and we can list all of them here. We put a termination character onto these, and the purpose of this is to avoid ambiguity. Otherwise, a suffix might be a prefix of another suffix. For this example, if we're looking at the ANA, that is also what this one starts with. So this one would look like a prefix of another suffix, but if we put the terminator character here, then that is not the case, then there's no ambiguity. Over here we have another example with a much larger sequence with the DNA alphabet. So this is the suffix. Here I talked about suffix trees. We take all our suffixes, then we build a sort of tree structure from all the suffixes. Our first suffix is called banana, right? So we start here, B-A-N-A-N-A. We have another one just called A, or N-A here. So the A would be this one here, and then there's the terminating symbol here. If you look at this, which is called the suffix try, we can see that there are some nodes where there are no options of leaving, right? So we don't have to make a decision as we traverse down towards the leaf nodes. The leaf nodes are the ones in the bottom. If there's no choices to be made, then we can collapse and remove this node. Then we take the characters for each of these labels and put them together. Then we have what is called a suffix tree. So here we collapse the N and A. We remove this one and make another label or another edge that contains the two characters. Okay. So when we have constructed a suffix tree, then per construction, that every internal node has at least two children. No two edges can start at the same node can have the same character. And as we go through this this tree, then every path specified a suffix. If you wanted to search for a suffix, then we can just go through this. Does NANA occur? We see, is this an NANA? No, no. Is this an NANA? No. Is this NA? Yes. Then we go down here and then we ask again. So if you wanted to search for a suffix, then we go from the root all the way to a leaf and see if it occurred. If you fell off the tree, then it would not be a suffix. If you were just searching for a pattern, then we don't have the requirement that we should end in a leaf node, then it's allowed to stop in one of the internal nodes. Okay, so this is a suffix tree and this is a suffix tree. Okay, so concluding this, let's mention the complexity. If you wanted to create the suffix tree, then it would be m squared in both the time and space, where m is the length of the sequence. When we're doing the query, that's very easy. That's just the length of our sequence we're searching for. So we just need to make n comparisons. If we're doing a suffix tree, then it's the creation and the time you need to, the time and space you require is only m, because you can collapse these labels. And when you're querying, you still only need to go through each character as you traverse through the three. Anyone that has worked with these kind of tree structures on a computer know how complicated they are, because you have a node and then you need to point to a parental node, and you have a number of child nodes. For each time you want to you have this kind, you need to have a pointer structure, so you need to allocate a number of bytes. You need to have 8 bytes for each pointer. And if you in a binary tree, you of course only have 2 daughter nodes. But you can have any number of child nodes here. Well, the size of the alphabet. So this quickly becomes very, very complicated. Not just to program, but also the memory requirement. There's a lot of overhead in this. So a human genome, which is around 3 gigabases, and because each character is a byte, then it corresponds to 3 gigabytes, right? 3 gigabase file would be, it's the same size. If you convert this into a suffix tree, then it explodes, and you require 45 gigabytes of memory. Okay. So tree structures are very, very complicated to work with, and they consume a lot of memory due to the overhead. You can represent any suffix tree with a suffix array. I didn't talk much about this. And the idea here is that you just have a matrix, which is, there's no overhead associated with this, But when you do the querying, then you actually need to do a linear search throughout the entire suffix array. Okay, so we didn't talk much about suffix arrays, and the reason for that is that we are going to talk more about this fantastic Burroughs-Wheeler transform. If we were doing, if we had endless resources and our computers were super fast and we didn't have a memory issue, then a suffix tree would be an optimal way of searching for queries, because you have all the information you need. But in practice, it's they consume too much memory, and if you consume too much memory, then all your programs will be too slow because they need to explore all this memory as it does the querying. So back in '94, I think there were two people, Michael Wheeler and maybe Matthew Barrow. I don't know their names exactly. So they came up with this, what they call the Burroughs-Wheeler transform. And this is a way to rearrange a string into runs of similar characters. So if you have multiple identical substrings in the string, which in our case is the reference genome, then this transform will transform it into some kind of permutation where there will be several occurrences with repeated characters. And when you have repeated characters, then it also makes it a lot easier to compress. So this was built for doing compression, and it's also what is the underlying engine in the bzip tool, which is standard on all Unix computers. Of course, it makes it easier to compress, but you can also decompress it, which is what I'm going to talk about shortly. And what is very, very useful here is that when you have this sort of Burroughs-Wheeler transform, then you can also do extremely fast querying without storing much more information in a lot less storage space than you would require from the suffix tree. Okay, so let's go forward here. So yeah, okay, so what is it? So we take a string. It could be this string here, AGACCCATGACC, terminating character. Okay, so we put this in a huge matrix. And for each row of the matrix, we do this kind of a cyclic rotation where we shift it to the left, and then the character that falls off, we put to the right. So it's this cycle. If you can imagine the string being wrapped around something round, and then you just turn it around. So this is what we do for all possible rotations. This is 13 characters long, so we have 13 different suffixes. What's in bold here are all the possible suffixes of the string. Okay. One thing to note here is that if we look at this G, for instance, and we wanted to know what preceded this G, what came before in our original string, then we just look at the last column. Okay, so we have a first column, I'll get a lot back to this, and we have a last column. If you wanted to know what preceded the original string based on what we have in the first column, then we look at what we had in the last column. Okay. So we have this huge matrix of all the characters. Then we sort these suffixes. And then we have something that looks like this. Okay. Since they're sorted, there's some structure to this which worthwhile reflecting on. We start with the terminating character symbol. Then we have a block that starts with A's. We have a block that starts with C's. We have a block that starts with G, and then a single T. Okay. And within the block of A's, we can see that we start with the C's and G's and C's. And this is because we have sorted them according to this lexical sort. Okay, so we have the positions here. What we write as post, that's position 1, that's the first position. After we have sorted this, this is our suffix array. We can see that the first one is actually the terminating symbol. If you look at the 1, 2, 3, 4, the fourth row here, then that's the full character. Then the last column of this Burroughs-Wheeler matrix is what is called the Burroughs-Wheeler transform of our original text. Okay, so let's get back to that shortly. So we have the Burroughs-Wheeler, we call this the last column, and we have the first column. Okay. So a question here is, of course, is the Burris-Wheeler transform of text, is that a permutation of the original string? The question is, of course, yes, because each of these represents a unique offset of our original string. So it is a permutation of our original string. Good. So the question is, of course, now we have our Burris-Wheeler transform. If we wanted to reconstruct our original string, there's an algorithm that shows the idea behind what we are going to talk about afterwards. So I'll go through this this algorithm. We have our Burris-Wheeler matrix from before. We have our Burris-Wheeler transform, and we have the first column here. This is sorted. Okay. We have our original string, and now we start to rank the occurrences of the different characters. Okay, so we, for each character in our original string, we say, is this what number of A is this? That's the first one, so we write A0. This G here, how many times have we observed the G before? That's also 0. Now we observe an A. How many times have we observed an A before? We have observed one more, so we write 1. So we do this ranking of all the characters. Okay. So I said before that if we wanted to know what came before the preceding character of our original string, then we could look at what was in the Burris-Wheeler transform column of our matrix. So if we want to reconstruct the string, we do this from the end of the read. So we start here with this simple. What comes before this one? Then we look at what we have here. That's a C. But we need to figure out which C it is. This is why we put the ranking. So for each of these, for the first column, I put the ranking as a subset symbol in this. For the first column, for the last column. So we start here, we know what precedes it, that's the 4th C, okay? Then we search through the first column for the 4th C, which is this one. What precedes the 4th C? This is what's in the Burris-Wheeler transform column. That's a C3. Then we go to C3, that's here. Right, so we did this by doing a linear search through all these. This is C3, and then we see what do we have here. It's this C3. What precedes this? This is what's in the Burris-Wheeler column. That's an A3. So we can build the entire original string by doing this kind of lookup table. I only did the first 3 or 4 here. Otherwise, this matrix will. This table would be full of arrows, of course, right? So it's just to show the idea of how this is done. In practice, this is it's not doable because we need to have a full table that as long as our original string that contains the offset. So there's a better way of doing this. This is called the FM index. Based on the Burris-Wheeler transform. It's called a fast minute index. And what this one does is simply a faster and more efficient approach of the walk left algorithm. This is all it does. The problem with this approach here is that we don't just need to store the Burris-Wheeler transform, we also need to store the entire first column, which is just as large as the Burris-Wheeler transform. So that's some overhead, and we also have this overhead of the ranking. So we need to come up with a more efficient way of doing this lookup. This is where the fast minute indexing comes in, and the idea here is that we need to figure out which A. That in this example, which of these A's does that correspond to? Because if we know which one it corresponds to, then we know what the preceding character would be. Okay, so this is what we want to do, and this would be identical to our walk left algorithm. The way this is done is that we build an index that tells us which character here corresponds to so which index of the in the Burrows-Wheeler transform corresponds to which index in our first column. But we don't really need to care about what the actual entry is here. We just need to know which row it corresponds to, because then we can discard the first column. Okay, so this is this is what is called the first left mapping. It takes which index this one and then tells you what the preceding character row is. Okay, for this, in order to do this, the FM index consists of two parts. It's the first one is a table that contains the occurrences of all the lexically smaller characters than a specific character in the suffix array. In short, it just tells us the position of character A in the suffix array. So if we were looking at the value of A in the C table, then that would just be 1, because the block of A's, we know that all these are grouped. Okay, so we have all the A's starting, then all the C's, and then all the G's. That's the C table simply gives us an offset for where the block A starts, where the block C starts, and where the block G starts. Then there's a function which they call the occurrence function, and this is in essence just the ranking. And based on the occurrences and the ranking, then we can apply this LF function to obtain the row number for corresponding that corresponds to a specific A. So an example here, we want to figure out which row this corresponds to. We know that this C should correspond to one of these C's, and we need to figure out that it belongs to this one, but we don't really care about this exact one. We just need to know the row number, because if we have the row number, then we know what follows before the C. So the FM indexing is a mapping from one row to another row that tells you which the preceding character should be. Okay, so the FM index, that is the Burrows-Wheeler transform of our text, and then a representation of these two table or functions. So let's do a quick example. We have our table here. This is the same example as before. The terminating symbol starts at 0, the A starts at row 1, the C starts at row 5, the G starts at row 10. Yeah, so yes, starts at, so it's because this is one index, this one, sorry, that could be a bit confusing. The T would be the last one that starts at row 12. Okay, so this is our C table. And then similar, we make this ranking function. This was the same procedure that I did over here manually. We make a table that looks like this. So we take our Burrows-Wheeler transform, and then we say we have a specific position and an A, then we want to know what the rank is. So for position 10, if we were looking at the A, then that would be our second A, so that would be the rank. So what the function does here is that this one tells you which block you should be interested in, and the occurrence function tells you the offset within the block itself. Okay, so you only need these two things to do this, and then we don't need to store the entire first column. Good, so let's do a short example of this. We're looking at the last column. This is row 6, so let's count 0, 1, 2, 3, 4, 5, 6. It's this one. Then we need to figure out which C this corresponds to. We can either just count the number of C's that we have, 1, 2, 3, 4, and then figure out 1, 2, 3, 4. Then we know it's here. Okay, but another, we could also use these functions, which is the way that the computer does this. Then it's using, it first figures out what the offset of the C is. That was a 5. 0, 1, 2, 3, 4, 5, it's here. And then the occurrence function of C6. Let's go back here. C and position 6. That's a 3, okay? And then it tells us that the first column of 8 would correspond to our C, so that's here, would be this one. But again, we do not care about the actual value in this column here. We should forget about that one, because we know per construction that this value is the same as this one. So we are just interested in the row number. Okay, so this is, we could do similar exercise with this one. Let's skip that. Hopefully it's clear. And then, good. So shortly, this is what the Burroughs-Wheeler transform does. It's incredibly confusing the first time you see this. It's also difficult to explain that. That's equally confusing. The way what it does is that it lists all the suffixes. Then you create the Burroughs-Wheeler matrix based on all these suffixes. Then you extract the last column. That's a Burroughs-Wheeler transform of your original text. Then you create your FM index, which is the occurrence table, and the C table, and that's all the information you will need in order to rebuild the your original sequence. Okay, that's all the information you need. Of course, the way we apply this is that we want to do to query a sequence. So after this slide, I'll talk about that. I mentioned the suffix tree and the suffix tree. If you're building an FM index, then the creation time is linear in M. Reversing it is also linear in M, and querying is linear in the length of the sequence. And what is really magic here is that we now go from an original human genome that has a size of 3 gigabases, 3 billion nucleotides. It's actually 3.1 or 3.3, right? So it's very big. And then because it's 3 gigabases, then it should also be uncompressed around the 3 gigabytes. But when you apply this Burroughs-Wheeler transform and build your FM index, then you can represent a full human genome to only 1.5 gigabytes, right? So it's an incredibly efficient way of including all the information of a full sequence. Okay, but of course we need to query this, and how do we do this? Similar to when we were going through the suffix tree where we had this kind of branching structure, then we can do exactly the same based on this walk left algorithm. Okay, but now we don't start from the end of our entire read. Then we use our Burroughs-Wheeler transform as a lookup table. Say we were searching for the complete query that is called GACC. Okay. Then we know that the first column per construction is sorted such that we have all the A's first and all the C's first. So what we do is that we jump into the block that starts with a C, okay? And then when we do the query, we do it from the back of the read. And so we want to figure out what precedes our C. In this case, we're looking for another C. So if we wanted to see what came before this C, we would go to the Burroughs-Wheeler transform to figure out what came before. So here we are searching for 2 C's. That would be the situation where both of these are C's, CC, CC, CC. Okay. So in the beginning we had 1, 2, 3, 4, 5. But after we have gone through the first Burroughs-Wheeler transform lookup, we are down to 3. So we could remove 2. Okay. And then you do this iteratively as you move throughout your entire query sequence. Okay, an example here, again, the same sequence. This is visually, I think it's very beautiful, very didactical. We start with a C, okay? Then we search for all those where the Burroughs-Wheeler transform is also a C. So in this situation here, it's the 3rd C, the 4th C, and the 5th C. Okay, then we go back and then we go look at our original sequence here again. So this would be our lookup for the second one, but now we are not looking for the C in the Burroughs-Wheeler transform. Now we're looking for the A, and here we can see that it's the first A and the second A. Okay, so we redo this this exercise. Each time, for the first time, we are when we're looking for the first character, it's a very, very large range that we're looking for. But as we move through these steps in each characters, we are narrowing the top and the bottom of these ranges. And in this example, we end up with 2 matches at suffix array 2 and 9. Good. So here it occurs in this position and in this position, and maybe let's see if there's a box coming up here. No. So that's GACC 2 and 9. This is what we see here and here. So in practice, and to my knowledge, in all implementations of reference mapping is based on this approach with Burrows-Wheeler transform. This is how it works conceptually. There's of course many small tricks that is applied to make it even faster, but these are implementation details. Okay, so this is how they do exact matching. But as I mentioned before, and as Lei will talk about very shortly, as I can see that I'm always overdue already, so I have one more slide, is that there's a lot of uncertainty. We can fix that. And so this is a figure from the BVA paper. Here they have a reference which is called Google, an query sequence called LOL, and then they are allowing for a specific number of mismatches. And what they do is that as they traverse through their suffix tree, this is a suffix tree, it's not a suffix tree, because you can see that each there's only one character on each label. Then as they move through the tree, then they keep track of how many mismatches they have, and they allow the search to continue down this path until they've reached this number. So here they allow for 1 mismatch. They're searching for LOL, so they start down by this branch. It's a G, that's a mismatch. Now we have 1 mismatch. We continue. O, that's correct. Okay, so we allow it to continue. We still have 1 mismatch. Now it's an O again. We wanted to have an L, so we cannot use this path, right? Even though we searched through and allowed for 1 mismatch. We do the same thing across this branch here. Right, we start with an O, that's a mismatch, we keep track of this. The next one is a G, that's also a mismatch, we want this to be an O, so we can discard this path. Then we continue down this path here, we started with an O, that's a mismatch, so we count this. Then we go here, that's an O, that's correct, but then we have a G, so that's incorrect, so 2 mismatches, so it cannot be down this path. We do the same here, we start with an L, that's correct. We have an O, that's also correct. Then we have a G, this is incorrect, right? So we can, and then our LOL string is not any longer, so we stop, so we did not have a match. So when we allow for mismatches, then we just allow the search to continue while keeping track of the number of mismatches. Good. Finally, open questions. If we are doing pad-end sequencing, then we can take into account that our fragment size is relatively short. It's only around 500 base pairs at most. Given modern-based sequencing, it shouldn't be any longer, so you can use this to our advantage when we do the mapping. There's of course problems with ancient DNA because we expect to have excess mismatches in the termini of read. This can of course be solved by allowing extra mismatches, but this will make the mapping a lot slower. Another approach is to discard the ends of the read when you do the mapping, but much of the ancient DNA is very short, so you definitely don't want to make a read that's only 30 base pairs even shorter when you do the mapping. Here we have said the genomic position, I kind of skipped that. The genomic position would be the value of our position in our suffix array. This is not a value that we keep because each character only takes up 1 byte, while each integer takes up 4 bytes. So if we wanted to store the position for each Burrows-Wheeler transform element, then that would be much larger than the data that we want to store ourselves. So in practice, this is applied by using what is called a sampled suffix array. So for each 25th position on the genome, then you keep track of this information about what the position is. And when you do the mapping, then you traverse back and see until you reach one of these sample positions. And this The thing that I did not mention, which is also relevant to mention, is that the purpose here was to make it very fast because we didn't have a lot of memory. We didn't want to use memory, but we had this huge occurrence matrix, which looks very, very big. In practice, this is not what we have. In practice, what we have is that we have this sampled occurrence matrix, where we keep track for every 25th position, then we only need to backtrack to that position to get the actual value. Good. And I think with this, yes, acknowledgements. Sorry for skipping through this, but I know that Leis is anxious now and he's looking at the clock. So this slideshow was prepared and based on a slideshow from Anders Krog that and one of my PhD students, Rasmus Hendriksen, made a subset of this and I modified it. It's always very complicated to make these kind of figures in and tree structures in PowerPoint, so I'm very grateful for that. The BDA algorithm and those examples that they are from the BDA paper, and the graph illustrations that I've used were taken from Wikipedia. Okay, so I think that's the that was the conclusion of the first part about how state-of-the-art mapping algorithms work in the context of high throughput sequencing data. Is there any question regarding this? Otherwise, we should move directly to Lei. So I'll stop sharing and then I'll see if there are any questions in the chat. No questions. So are there any questions that people want to ask here? Was everything clear? I know the Burroughs-Wheeler transform is very confusing in the beginning, right? So I hope this was useful and might serve as an introduction if you want to read more about this. Okay, good. Okay, so Lei, should I introduce you about what you're doing, or do you just want to start?
No, I just want to start.
Okay, sorry. Okay, good. Okay, so I'll can you share your screen? If that works, then I'll kill my my microphone. Yes, good. Thank you. Please move on, Lei.
Yeah, so I can say actually you efforts talking, so no worries. I think I can handle it. So thank you for inviting me here. And today I will mainly talk about the uncertainties in the NGS data. Oh, sorry. So here's the outline for my talk. So basically we will touch the concept of the base quality, MapQ score, genotype likelihood, and the QUAL score. So for the base quality score, actually you can find it in the FASTQ file, SUM file, and BAM file. And it is like a base level uncertainty, tell you like how reliable a certain base rate is. And this MapQ score, you can find it in the SUM file and BAM file. And it is in a rate level. So basically for the whole rate, actually you only got one this kind of score. And this basically tell you like how certain the rate is origin from your aligned position. And you also got this genotype likelihood, which may be this 3 integers. And it is in the individual level. So basically it tell you like how certain or how likely this individual actually get at this site actually get this genotype. And finally, you have this kind of QUAL score, and you can also find it in the VCF files like this value. And basically, this will tell you like because you got a bunch of population, a bunch of persons or a bunch of individual samples, and this tell you like how certain this site is a SNP site, or how certain this site is an invariable site. And through my talk today, I will mainly talk about the two concepts here. And the base quality score will serve as a preliminary information for the MapQ score. And the QUAL score will serve as a basic application of the genotype likelihood. And before we diving into the biological area, let's first do some math And so when I say max, basically I mean this Bayesian theorem. So suppose you have like two events. One is called A, another is called B. And the probability given B happened, the A happened, is the joint probability A and B both happened divided by the probability B happened. And you can switch the position of event A and B and get the probability given B happened, A happened, multiply the probability A happened, divide by the probability B happened. And you can do some further tricks and you can get this kind of thing. And specifically, if we treat B as some experimental observation, like kind of like from a specific site, if we say a bunch of base calling rates data, and actually we can calculate this kind of posterior probability. So the probability of A here is called the prior probability of event A happened. And here, given you see the observation, this value actually is called the posterior probability given you obtain some kind of experimental observation. And this value, probability given A, the probability of O actually is called the likelihood of A. So for the posterior probability, we will mainly touch this concept in the Meteor score. And for the likelihood of A, we will mainly touch this concept in the genotype likelihood section. And I will talk more about genotype, about the likelihood concept here. So for the likelihood, we mainly use it in two ways. One way is we compare with like this X basically is the observation, and theta basically means the model parameters. So this is a probability given this parameter sighting, and if we observe some specific like observation. And we just compare with the values of two likelihood function. And if one theta, one is gave you maybe a larger likelihood compared with theta 2, that means the parameter sighting theta 1 can better explain the observation. So this is a basic idea of maximum likelihood. And the other way to use this likelihood function is actually to calculate this kind of posterior probability, right? So, but if you compare these two, actually you will find one funny thing. So you don't need to care much about the absolute value of likelihood. What you really care is the relative value of likelihood. So here you just want to know that this value is larger than this value. And here you just want to know the ratio of the likelihood function. So basically, if you do for the likelihood function, you just divide them by the same value, you will get the same kind of sense of model prediction. And so this is basically what I want to say here. And suppose mathematically, people always calculate the log likelihood to make computation easier. And if you do in this way, the rescaling of the likelihood function become just subtract some constant value for all the likelihood function. That will not change any result of your downstream analysis. And I will move on to the biological part. So you just learned about this kind of fantastic BWT algorithm. So ideally, if I gave you a lot of short rates data and I gave you a reference genome, you will for each of the short rate, you can find the position. Maybe this short rate is actually origin from this position, but this is just the ideal situation. If you allow some kind of tolerance of mismatches, you'll find that along a genome, there'll be different positions you can map this maybe one specific short rates. This is because of both the biological similarity and the structural similarity of the DNA sequence. So when I say the biological similarity, I mean along the genome, there'll be certain regions actually repeat again and again due to some biological or genetical reasons. And so if you just happen to need to map a short race origin from such repeatable region, there'll be several possible positions actually you can map this short race. And there are other reasons like the structural similarity. So even though you don't have this kind of biological repeatable region, or you just randomly have a race actually here, it has nothing to do with the repeatable region. But because actually the genome is just made up by 4 nucleotides, if we also take into account the insertion, deletion, there'll be only 6 different elements to comprise this whole genome. So given that the genome is quite long, like the human genome is 3 gigabase pairs long. So once a while, you will find some quite similar patterns occur again and again. This is just due to the simplicity of the elements. So no matter biological similarity happen or structural similarity happen, you can easily find that there'll be not only one unique position you can align your short race. And what makes things more complex is actually for the data. So for the short race data, if it is modern, it'd be like 75 to 150 nucleotide long. And if you go to Asian data, because of this deamination and some postmodern damage, actually, you'll get the short race actually always maybe located around 40 to 60 base pair long. So if you align this kind of thing to the quite long reference genome, you will find more like this kind of suspect aligned region rather than just one. And that's why we want to introduce this kind of MapQ score to access which position is the best position and how certain we are sure that this position is the right place, or which this position is this short race actually origin from. And let's go to the biological similarity and this structural similarity one by one. And suppose now actually we have this kind of biological repeatable regions, and we happened or we are unlucky try to align some short race actually within this kind of origin from this kind of repeatable regions. And which position actually you think it is the best position for this short race to align? Perhaps most of us will think that because this is just one mismatch apart from the reference, and this is also one mismatch apart from the reference. And suppose we only got one perfect match alignment here, and most of the guys will think this position should be the true position for this short race data. But let's look at this mathematical calculation. So suppose actually we have a short race with X with a length L and origin from this part. We just origin from this short genome, and they are only like n+1 different possible positions for this, but only one actually is perfect aligned. The others are just one mismatch apart from the reference. And this actually gives us the probability of it is true from this region. So this P given XR0 basically means actually a prior probability, like this guy actually from here, because we have n+1 positions. So this value actually is 1 over n+1. And this value, we just gave actually because of for the short race, there may be some kind of a sequencing error, or there may be some kind of there may be some kind of sequencing error and maybe some kind of PCR replicate error. So if you observe the short rays have a G at this position, we assume that there will be like a P/3 probability. The true rays from this region, from the true region actually is A, and the P/3 is C, and the P/3 is T, and 1 minus P is this original rate actually is G. So this actually gives you some kind of the base calling error, but I will go back to this later. And given this kind of thing, so we assume that uniform this kind of error along this genome, and we just calculate the posterior, like we know the reference genome, we know the rates, and what's the probability that this position, the perfect match position, is the true position. We can get this value. And if we divide all this kind of thing by 1 minus P to the power L, we get this one, and do some Taylor expansion, we get this one. And suppose we set this kind of calling error, P equals like 2%. And suppose we have this, along this genome, we have 150 repeatable regions for this short rays. And what we can get is this short rays actually origin from this region. The perfect match region is only 50%. If the numbers of repeatable region increase to 1,000, the probability it come from this region will be 13%. But I give you an example for the allele repeat in the human genome will be about 1 million. So if you are unlucky, just want to align short rays from the allele repeat region, there will be like 1 million possible positions you can align. And if there's only one, this kind of perfect match position, and this value can be very small. And if you are even unlucky, so they are not just one perfect match position. And you can see here, suppose there are two not perfect position, then here you should multiply a 2, and the probability should be always less than 50%. So if you got like 1 million allele repeat, then this value will be even less actually. Yeah. So this give you a sense of the biological similarity. So let's go to the structural similarity. So we will talk about another situation. So previously we assumed that the short rays actually come from this genome, but suppose there are some contamination, which is very common in the Asian DNA study. So suppose you analyze some human material, but some virus material actually kick in, and they are remote from each other. And we just want to know like whether we can find a position actually along the human reference for the virus. Ideally, there will be no that position, but due to actually the simplicity of the elements that make up the reference genome, for the virus or even for some unrelated species, if the short rays are really short, you will always find some positions for them. And imagine that we are do something in an extremely case. So we have a short rays of the length L, and which is just from maybe external organism, not from the endogenous genome. And we want to map this to the endogenous reference. And so the extreme case is the reference genome is just like a random shuffled genome. So basically, for each position, there will be like a quarter of the chance to be either A, C, G, or T. So in this case, we can also calculate like for a specific position, what's the probability of short race L has a mismatch K. And this is very easy to be calculated, just like binomial distribution probability. So it calculate like this. If they allow that, there will be up to like m mismatches, and the probability of a short race with a length of L will have this probability to map to a specific position with the tolerance of the mismatch up to m. And if we go along the whole genome, like assume that the whole genome of a length capital L, and the expectation of the position that can map this specific short race will be this value. So this you have already seen some similar patterns in Toffin's presentation. And if you assume that actually L is much larger than small l, and this value can be approximate to this value. So let's say, suppose you have a external short race and you want to map to the endogenous genome. And what's the probability that you can always find a position to map this short race to this genome? This is a probability for a 1 minus f. What I mean here is a probability for the short race cannot map at a specific position, like given that you allow up to m mismatches. And if you go along the whole genome, this will be the probability that this short race cannot map to any of the positions along the genome. So if you use 1 minus this probability, this will be for a specific short race, the probability it can map to at least one position along the genome. So if you do some math trick like this, because we know that f actually equals E over L, and we know that actually L is very large. So based on the limitation theory, we can actually approximate this value to be something like this. And this can be plotted like this. So all the solid line here is what we calculate the theoretical result. And this star here basically means we map the equine genome to the short race, to the human genome, what we get. So basically they are quite close to each other. And as you can see, as the short race become larger, actually the probability it can map to the human genome will become smaller and smaller. But because actually our Asian genome is maybe in this region, so actually for some of the short race, actually we cannot distinguish whether it is a bacteria or virus or it is a human by just using this kind of method. Or at least what we can say is we can find some positions for this kind of external short race data. So even there's like this perfect match, or maybe even we know that there are some positions can align the short race, we can neither say this short race from this endogenous genome, or we can not say this is the right position for this short race. So the best way for us to move on is to embed our assertion, not just rely on this kind of rely on this perfect match, but rely on some framework of probability. Before we move to the MAC-Q score, I'd like to first define the base quality score. So here is something you maybe find it in a FASTQ file. And the first one basically is the short race data. And the second one is this base quality score. And this is ASCII code, like this kind of thing. So, this corresponding to this ASCII number like this. And 33 is actually the first visible or maybe first printable ASCII symbol. So that's why actually we choose this guy as the starting point to show the quality score, and the quality score corresponding to this Q score. And Q score actually is just a offside of the ASCII ASCII number. So basically, this bracket basically means 7 and something so on and so forth. And so basically, this is also called like Fred scale score basically. So it defined as this way. So Q here, 10 to the power Q minus Q over 10 basically define the probability that if you observe a short rate is A, like here, and what's the probability? It not this short rate is actually base rate is not from a true region that it is A, and this is a probability that suppose you observe a short rate A, and the true rate is also A, which is 1 minus epsilon. And so this is a way actually from the Q, you can calculate the error. And also you can from the error to calculate the Q, but remember Q is always an integer. So you always, when you calculate this value, you always need to round about it. So I'll explain it more clear in this slides. So this is a fast Q file, and suppose you map it to the genome, and there are two regions actually got quite similar short rates. This is in the genome reference. So you can say actually only this position for this alignment is different from the short rates. And for this alignment, actually you all got like two different positions actually different from the short rates data. So what's the probability? Actually, you actually this guy is come from this guy. So this rate actually base actually come from this rate, which is because we know that I, if we search here, I equals yeah, we cannot say I, but I actually is 40. So that's why the quality score here is 40, and we just put the Q here is 40, and to calculate like given we observe a G, what's the probability it come from a region which is A here. So if you calculate this value, they'll be like this value. So like what they gave, the example gives to you. And suppose for this rate, so suppose you observe a G and the true rate is also a G. No, sorry. This is, so the probability, oh, sorry. So the probability of this is actually this value. And if you go 40 here, you'll get like this value, like 0.9999. And let's go to another position. And if we see this one, the origin, the rate actually have a rate G here. And for this position, it is a G. And for this position, it is a C. So if the rates come from this position, and we will get actually, we observe a G, and the true is G, the probability is around, if you calculate this value, is around 0.8, and this value will be like 0.066. I should remind you about this assert, because they are, if you are the same as the rate, then it is only a G. But if you are not the same as a rate, it can either be A, T, or ACGT. So basically it be ACT, right? So for each of them, actually they have, we assume they have the same chance to be each of them. So that's why we have a assert here. And similarly, you can calculate the probability of this one. And this is the origin, the definition of the base quality score in this way. So epsilon can be right in the Q score way. But I just want to remind you here, if we assume that the observation prior probability of observation like ACGT had the equal chance to be obtained, like prior probability if a observer A equals a false and probability of C is also equals a false, we can switch the position of observation and the true. So like this, and this actually will lay the basis of the likelihood function, genotype likelihood. So I will come to, I will change my presentation into this definition afterwards, like when we discuss about the genotype likelihood. But now we just do this. So we observe a rate and we just to infer the true position. So we come to the last slide of the MapQ score. So as we discussed before, there will be like a biological similarity and also structural similarity. You can, I just remind you the biological similarity is just like the rates actually come from this reference material, but maybe there are some repeatable biological regions you can map this rates in. So actually this is this part. And if the race actually is come from external algorithm and you just map it to a reference genome, it is this part. And I just go through it. So basically here means you have a rate and you just want to know that whether it come from a specific position along the genome. And you will get this kind of calculation, and this is actually obey the Bayesian theorem. This is a prior probability. If I give you a rate, you just guess whether it is from the human or it is from the virus. So this is called the like maybe the contamination rate or something. And this is assume that you know this short rates actually come from human. And what's a prior probability? It comes from a specific location. Assume that we have like maybe totally L location along the genome because the genome is like L long. So this value will be 1 over L. And this part actually is just like you multiply all the base quality score together, like this kind of thing. Multiply them together regardless of this false. So the things above the numerator actually gives you the probability that gave you a rate and it is come from human and it has it mapped to the position little l, and we know that the reference genome. So when we know the reference genome, actually we can calculate each of the map quality score stuff. And the things underneath divided into two parts. One is whether these short rates are come from the external genome. So this is a prior probability. It comes from external genome. This is a probability that although it is come from external genome, you can still map to the human genome. And this is a probability that it comes from the internal genome and you map to some position of the genome, not the position is not specific. This is a position specific. So we know that it mapped to the position little l. So once you calculate this thing, and if you do some trick, you put this previously when we calculate the structural similarity, actually we got this a false multiplied together. If we divide the false to this probability of this kind of map quality score multiplied together, we can get this kind of value to make the computation simpler. But the basic idea is the same. And based on this kind of thing, you can know that for a specific rate, where the probability it comes from a specific location along the reference genome. And this is this. And if you use this one, and if you use the Fried scaled method as what we discussed before, like you calculate this one and you calculate like 10 to the minus some q over 10, and you calculate the q to make sure this value equals that 10 to the minus q over 10, and you can get actually the map quality score like what we showed before. So this is what I said about the MapQ score here. And when you get this, this is a specific way to calculate the MapQ score. There are other models to calculate it. And this MapQ score can be used by either tell people like how certain this precision for this alignment is. And another thing is actually you can use this one as a assessment measurement to do all this BWT alignment and to find the potential positions for one-shot rates. So now we come to another concept, which is genotype likelihood. So the genotype likelihood is different from the MapQ score. So now assume that we pair up all the short rates along a reference genome. And for each position, actually, you will get a lot of base rates data. Like for maybe this specific position, you'll have like maybe, if I remember right, 10A and 1G, or maybe 11A and 1G, I forgot. And so if I ask you like, if you get this kind of data, and how can you tell me the genotype here? And suppose it is a haplotype, maybe people will guess it is an A here. And suppose it is a diploid, how you can tell me? Maybe you say this maybe 11A or 10A, you will say that maybe it is a homogeneous AA here. And this J is just due to the sequencing error or something else. But maybe as we proceed, as we move on, I will show actually, even you observe this kind of data, you can still maybe actually the heterozygote JA is the most possible genotype underneath. Suppose actually this is just we have already aligned it, but actually we don't relate it any error framework to this kind of data. So because actually for the apart from the base calling error, actually we also get some kind of position specific error like the sequencing error. So if you look at this specific FASTQ file, actually for each short race, actually they start with some race of higher quality and ends with some race with lower quality. So this higher quality and lower quality actually will also affect the guess of the underneath genotype. And if you take into account the Asian genome, there'll be something like postmodern damage. This is also position specific damage. Like you will say actually at the 5' end, there'll be a lift of C2T change. And at the end of close to the 3' end, you will see a lift frequency of G to A change. Apart from that, the Asian DNA are always bad preserved. So it has a very low rate depth. So suppose I only give you for this specific position, only one short rate A, how you can guess a diploid type like genotype, like maybe it is a AA or AG, you don't know. But based on the genotype likelihood, we can kindly, in principle, solve this kind of problem. So let's talk about the idea of genotype likelihood. So the genotype likelihood is defined as likelihood. So it is in probability framework, it is given like we know some specific genotype, what's the probability we observe the observations, like the short rates, like the rates actually pair up to this site. And suppose like we need to know like for a specific site, how many genotype we need to calculate. Suppose for the site, for one specific site, and the algorithm is a haplotype, the answer is 4 because this G can only be ACGT. So actually the likelihood will be the likelihood of this specific site have a true genotype A, true genotype C, true genotype G, and true genotype T. But normally we will analyze data with a diploid organism. So for the diploid organism, the answer is 10 because they actually don't care much about this kind of order of the genotype. So basically, in my context, AC and CA are the same. Just because easy to understand, we actually order them in the alpha beta order. So basically, we will chart away the CA but keep the AC. And if we build up this kind of matrix, we can count the upper triangle of the matrix. There will be only 10 possible genotype, and we will calculate like 10 possible genotype likelihood. In January, suppose you have an algorithm with a genotype like N, with a plotting of N, and the number of genotype you need to calculate is N plus 3, choose 3. I can give you an idea of how to calculate it. So basically, it is just like you try to align the maybe for the diploid for the ploidy 3, you just try to align maybe 3 circles, same circles, and 3 same triangles. These 3 same circles basically means the 3 chromosome or 3 site actually nucleotide. And this triangle here is just try to divide whether it is A or whether it is a C, whether it's a G or T. So if you are like in advance of the first triangle, it means nucleotide A. And if you are between the first and second triangle, it means nucleotide C. And if you are between like the second and the third, it will be a G. And if you are after the fourth, the third triangle, it will be a T. So like this. So basically, this kind of thing means the genotype ACG. And if you go to like the ploidy level 4 case, this alignment basically means the genotype CCGT. So if I give you another case, so basically we try to realignment this kind of circles and triangles again, and we can get this now means CCG because both of these circles actually between the first and second triangle, and the underneath case become ACGT because for each of the region actually you get 1 circle. So basically this will represent ACGT, and the N plus 3 true 3 actually just tell you how many this alignment actually exist. So for N equals 3, you get something like 6 true 3. And for N equals 1, you get 4 true 3, which is 4. And for N equals 2, actually you got 5 true 3, which is 10. So basically this formula works. So we now know how many genotype likelihood we need to calculate for a specific site. Now we need to know like some different models of how we calculate the genotype likelihood. I will first introduce you guys the simplest one. So this is actually the original GATK genotype likelihood calculation. So based on their calculation, they assume that for each of the rays actually pile up along this side, they are independent. So if we observe like ACGT for a specific site, we can just multiply all this kind of probability or likelihood together. So OI here just means a single base calling or a single base rate. So OI can be A, like suppose we, for a specific G, like maybe AA or something, OI can be A, C, GT, just that you observed each single base rate. And as I said before, now we change this one actually is a true value, and this one actually is the observed rate value, but it is still based on the base quality score. So epsilon I and this 1 minus epsilon I, we can just use the previous base calling score to calculate it. And sorry, this one should be 10 to the minus qi over 10. I didn't realize there's a tempo here. And for the haplotype one, actually the G is ACGT. So we just use this kind of base quality score and can calculate this value. But if it is a diplotype model, like the G can be AA, AC, this kind of thing, then we should say that we should split this value into two parts, like whether this OI is come from the first nucleotide from the genotype, like suppose you got the AC, whether this OI actually is come from the A, or whether this observation is come from C. So then we just calculate it based on this Bayesian formula. And if we assume that the observation have no preference to be the first nucleotide or second nucleotide, which we call it, there's no reference bias assumption. And then actually for a specific rate, it come from the first nucleotide of the genotype or the second nucleotide of the genotype will be a half and a half. And you can just multiply them together. And this part actually is the same as the haplotype genotype likelihood. And this is the formula way. And if you want to calculate it in a matrix way, it looks like this. So this is all possible genotype. And here is the maybe a specific base you actually observed. So this value actually, if you multiply this row with this column, basically this means the genotype likelihood of AA if you observe a single A rate. And here, similarly, suppose you multiply this row to this, which means actually the likelihood of genotype AA if you observe a single C rate. And once you get all this kind of rate along the just pile up in one side, you just multiply them together, you get the genotype likelihood for this specific position. And maybe I gave you an example how to calculate it for a specific example in a specific case. So now I know that there are 11A and just 1G. And let's assume that all these 11A actually got the quality score plus. And let's check the plus. Plus is corresponding to the Q score 10. And we only got 1G, but this G actually got a quality score I. So I, as we mentioned before, has a quality score of 40. So now we know that we actually got 11A and 1G, and I will call all the 11A observation from 1 to 11. And the single G will be observation 12. And we want to calculate the likelihood of this. Previously, we defined the likelihood as a multiple, but because I use the little l, what I mean here is a log likelihood. So we just add them together. And because the genotype is a homogeneous, because we now calculate the homogeneous AA, so remember our previous calculation, there's a half and half. But suppose this is AA and this is also AA, the value are the same. So a half and half collapse to just one value. That one value is actually given the nucleotide is A, and what's the probability you observe a G, and given the nucleotide is A, and what's the probability you observe a A. And this actually goes back to the base calling error. You just do this, and as I said before, plus means 10, and I means 40, and you calculate it, you can get some value like this. And this is a log likelihood. And if you want to calculate the flat scale likelihood, which means previous, like suppose we calculate the true likelihood here, and we let the true likelihood equals 10 to the minus q over 10, and we calculate that q value. The q value is an integer, so actually we should round the fraction, and what we get is this likelihood of AA is about 50 in the sense of flat scale likelihood. Yeah. So let's do another round. Like if you want to calculate the homogeneous genotype GG, and based on the same observation, and you got this one and this one because they collapse and become nucleotide G and nucleotide G, and you can do the similar calculation. But now the G is a true genotype, and so here previously is epsilon over 3, now is 1 minus epsilon. A now is maybe because of the calling error or something, so it becomes epsilon over 3, and you can do the same calculation, you get this value. And for the flat scale likelihood, it looks like this. So we do this kind of homogeneous calculation already, and if you follow the same kind of way, you can do this. And then we should calculate a genotype likelihood for the heterozygote AG in this case. So for the heterozygote AG, you just do the same thing, but now you cannot do the collapse trick. Now it has a half of the chance this G come from A, and half of the chance this G is really come from a G. So you do this, and also in this part, you also get this kind of thing. And if you just calculate this kind of thing and this kind of thing together, you get this value. And the flat scale likelihood of AG actually equals 39. And so now you get all 10 likelihood function. But if you are familiar with VCM files, actually VCM file will not give you all these 10 values. Most of the case, it will give you 3 values, but for some SNPs, it will give you like 5 values. So now, actually, I will let you know, because actually in this all 10 genotype likelihood, some of them actually are same with each other. This is because we only observe like A and G in the short rates at this position, and we didn't see any C and T. So any genotype related to C and T should be symmetric. So if you see the genotype likelihood like CC and TT, they have the same value. CT also have the same value. AC and AT have the same value. CG and CT have the same value, right? So actually, the invisible like genotype or nucleotide actually will be symmetric with each other. So we write the previous genotype likelihood like this, and this is the value we calculated. And because we just call the star invisible nucleotide, and we rearrange it by reference, alternative, reference, invisible, alternative, invisible way, and we can comprise the information of genotype likelihood to this value. And I didn't mention before, the flat scaled likelihood are like the log likelihood. So as I said before, the absolute value of likelihood or log likelihood doesn't matter that much. So you can subtract common constant for all the this kind of likelihood, and to make it smaller in some sense. So the trick in the VCFI is you try to subtract a common constant to make the largest, the smallest genotype likelihood to be 0. So if you, like for this case, if you subtract all this value to 39 or something, you get this value. And this value is look more like what you will observe in the VCFI. And if you really go to the VCFI and calculate the genotype likelihood, actually, you will observe another value. That is because actually VCF tools calculate the genotype likelihood, not as we expect. It is not used the simplest form as a JATK. It used this kind of form. So this is a likelihood for you to calculate the genotype likelihood of a heterozygote in the BCF tools. And this is a likelihood when you calculate the genotype likelihood for homozygote genotype. And this part, as you see, basically this is just a binomial probability. And this part are quite similar with each other. And the right part here is because VCFS, unlike the JATK, it don't assume all the rays are independent with each other. It said like maybe the if you observe quite a lot of rays, and the rays actually become less and less important. So suppose you observe like maybe 10A or maybe 30A or something, and the first A actually matter more than the last A. So this is basically mean that. So suppose it is a first A, K equals 0, and then this value actually is 1. And suppose it is a 30th A, and this value may be very small, this part, and that only weight 0.03. And why, you ask me maybe why this value look like this? This is empirical. And this is just from actually the BCF tool. They just hard coding this into their code. So we have no idea why this come from, just from empirical at their maybe error or something. And we believe that maybe this can be changed by some advanced model. And this part basically is also rate dependence part. I think I show it in a second slide. So this part is also rate dependence. So basically this, if we forget this 0.97 multiply this kind of thing, and just look at this part and this part, this basically means if the number of error rays is larger, when I say number of error rays, I mean, suppose you observe A, and but you see something C here, and so the C actually is a error rate basis. And the number of error basis is a probability, it is larger than K plus 1. And this is a probability that the number of error rays is larger than K. And this describe the contribution of the K plus 1's rate contribution to the probability. And because this is rate dependence, you cannot simply say that we just randomly use this kind of rate. Suppose for this side, you got maybe 2A rate and 3C rate, 4G rate, and 1T rate. And because the one actually, maybe the first one count more, so we tend to put, or they tend to put the rates of best quality at the first position. So we should, when we calculate this kind of genotype likelihood, we should first sort all this rate as this. So basically, this is a best A, and this is a second best A, and this is a best C, this is a best G, and this is best T. And according to this, after this, we calculate this kind of value because the order matters here. And this is only two method model actually just use the raw base calling error to calculate the genotype likelihood. But the genotype likelihood have a lot of other models. They will use this kind of recalibrate base calling error or mapping quality or other things like the reference bias stuff to calculate. I will go through the model, but I will not go into details about the model. So we first talk about our very easy one, simplest one. I have already tell you. So basically, there's no reference bias, and this is just a single base calling score, and you just use this one to calculate a single race genotype likelihood. And if you assume that they are independent with each other, you just multiply together, you can get the genotype likelihood of a specific site. And this is the second one, BAMF tools, SAM tools, MAC, and also the BCF tools calculate the genotype likelihood. They assume this kind of rate dependence, but underneath the reference is, they also assume reference, no reference bias. And yeah, and another thing is actually, they assume the error occurs, but the error will not affect the major and minor alleles. So there's no error for the major and minor allele. The error is just the come after the major and minor allele. I can show you maybe more clear here. You get a half here. You don't have a half multiply some epsilon or minor some epsilon. So there will be no error at the major and minor allele there. And then we go to something they will use this recalibrate stuff. So for the soft SNP, actually they use the raw quality score, but they also take into account the rate position of the base and also the base context, like whether it is a C, whether the base is a C or T or G, or maybe the base is a C and rate is a T, this kind of thing. And because this soft SNP is also come from the nearly the same group as a BAMF or SAM tools, this kind of guys. So actually they also assume some kind of rate dependence, but they use different values, not as the 0.83 and the 0.83, 0.97 as the BCF tools. They use another side of the parameters. And there's this Kim guy from Nielsen's lab a long time ago. And when they calculate that, they actually just use the map, the major allele, minor allele, and two invisible allele, basically, and assume no reference bias. And the interesting thing here, actually, when they estimate the error, actually, they don't estimate error from the base calling error from the alignment, but they actually estimate it from external source. So this is from some external sources. And so I don't think this is quite accurate. And there are other methods like this value. This method, it takes into account the raw quality score, rate position, base context as what we said before, but this guy actually do a regression and to recalibrate some kind of adjusted base quality score and use that one to calculate the genotype likelihood. But underneath their model, they also assume no reference bias. And but now actually the base calling score has something to do with the position. So it is a position specific base quality score. Yeah. Oh, sorry. So actually the Wigman's paper or the Alatas, right? Actually they plug in kind of postmodern damage matrix. So now, because they take into account this kind of a lateral C to T change, remember I said to you, and also G to A change for the Asian DNA. And apart from this reference bias matrix and this base calling error matrix, they plug in one this kind of postmodern damage matrix, and they estimate the whole picture of the genotype likelihood in the context of Asian DNA. They take into account the raw quality score, position in a short race, and they also take into account, like suppose you got a reference, the nearby reference nucleotide, like suppose they take into account AC, CT, the adjacent like nucleotide, rather than just use one nucleotide to estimate the error. And the last one, maybe the most recent one, they try to assume that there's some reference bias. So if you observe a short race, it may be not just an equally chance to go to the first nucleotide and second nucleotide of the genotype. There will be some kind of combination, combination. We just need to assume that AI plus BI equals 1, and they just try to estimate. Suppose we have this one. Maybe some at maybe 60% of the chance it goes to the reference genome, 40% of the chance it go to the non-reference allele actually for this SNP-AD method. But they also like to calculate something, recalibrate the genotype likelihood. So after we go through all the concept of genotype likelihood, now we just have a quick discussion about what the genotype likelihood can tell us. So there are a lot of applications based on the genotype likelihood. So mainly about the inference, like we inference the phylogeny of different individual, or we inference like the population size or maybe population history of maybe one population or two populations. But I will just touch the very shallow ones. The first one, because the Bayes theorem, suppose we know the genotype likelihood here, and we know the prior probability of each genotype. Suppose we assume in a very naive way, each probability will, each genotype will have the same chance to occur at a specific site. Then the largest genotype likelihood corresponding to that genotype actually is the most probable genotype at this position. Or we can say that that genotype actually explains the observation best. And so if we see this kind of genotype, as I said before, like this kind of thing is like a Fred scale of the genotype likelihood. And this 0 basically means the largest genotype likelihood. So as we calculate previously, this 10A and 1G, 11A and 1G, and the base calling error is plus for A and I for G. And actually, the heterozygote genotype AG is the most probable. Or I gave you the data, you should and ask you to like guess the genotype, you should give me AG rather than GG or AA, right? This is against the intuition, just do the count. And for both BCF tools and also simplest genotype likelihood, you always get this heterozygote genotype to be the most probable genotype. This is the first application. And the second application is about this QUAL score. So I don't know how many of you actually are familiar with this kind of coalescence theory. So suppose you have a lot of individuals here, and you have this kind of individual, and you just can construct a coalescence tree. And this M here basically means for a specific site, you just calculate like the expectation number of new mutations occurs along this tree. Maybe I can explain it more clear. Like this K to NE here, basically you can just mean like the population size, or suppose just the population size. And in population genetics, it is called effective population size. So if I go deep, it is basically means the population that a Bay-Wright Fisher model. And little n here basically means the sample. So suppose you got n diploid type sample, and you will have like 2n chromosomes, like this kind of thing. And actually, this value you calculate here is the expectation branch length of the branches along this tree. So basically, I mean this plus this plus this plus this plus this plus this, and mu basically here means the mutation rate. And so if you do some kind of simplify of this formula, you can get this kind of thing. And this one is very famous, which is called Watterson's theta, and can be also inferred just from the sample and by pairwise comparison. And this is a harmonic sum of this this branch or something, the number of branch. And so all this actually means how many the expectation number of mutation occurs. So we assume that actually this mutation occurs by a Poisson distribution. So this part is a Poisson distribution. And this part actually is, suppose let's go to the detail of this. So for fx actually estimate the frequency of one specific allele, and in the population, fxi basically means the frequency of that specific allele in a single sample. And this value actually is calculated not just by count, but use our base quality score. And when you do this kind of thing, it is called effective base depth. You can treat this as just a singular count. Like suppose I observe A and observe 2A, and just here is 2. But in this way, actually, you observe A with a quality score like 30, and the other A is with quality score 2. That means actually that 2 doesn't matter that much, but the 30 really means something, because the 30 are of good or of better qualities. And based on this, you can calculate something like the frequency given, assume that actually only a subset of the nucleotide is the true evolutionary signal, and the other actually is due to, suppose this as basically is AC, and but you along this sample actually you say ACGT, and this AC basically is you assume it is based on because of the evolutionary process, and GT maybe because of this kind of sequencing error. We just want to test how large is this S. So how large the evolution process can explain the variable, and how much the sequencing error can explain the variable. So when we calculate the subset of the total nucleotides site likelihood based on calculate the likelihood based on the observations, it is look like this. So for this part, basically is our genotype likelihood for one individual, right? And this part is just the way we choose, we calculate the condition frequency from this evolutionary subset, and we can calculate the likelihood of for one individual whether the variable observed from this one individual actually is can be explained by this subset, and we can also multiply them together, which means actually all the individuals variable actually can be explained by this subset, and this part, as I said before, is the probability of prior probability of the large of the subset. So R here, I guess, is the number of the possible mutations, because actually they are, I should say that they are, suppose you observe like S equals maybe 10, only 9 are derived mutations or alleles, and 1 is actually origin allele. So you should subtract 1 here. And once you multiply them together, what you get will be a posterior probability of S. So basically that means, given that observation, the subset that can be explained by the evolutionary process. And if you calculate that, if you observe a variable site, and if you calculate the SNP, the probability whether it is if you observe a site and you you have different kind of race for different individual, and you can calculate the probability whether it is a SNP. You can basically depend on this kind of thing. You can calculate it like this, and if you do the Fret scale trick, you can get this QUAL Fret scale trick, and to say whether it is so whether an invariable site is really an invariable site. So basically what we calculate here is like an error. So based on the observation, we think it is an invariable site, but we just calculate the probability this invariable site is a variable site. Or maybe we can do in another way. So we observe a variable side, but we just calculate the probability whether it is an invariable side. And this is called the QUAL score of this variable side. It is like error. So if take this as an example, so we actually observe alternative A here, and so we just want to confirm that whether this is a variable side or this is an invariable side. Based on we have already observed A, so this should be a variable side. So the QUAL score is 29, which is not that small. So that means actually we kind of sure, or in 1 minus 10 to the minus 2.9 chance this is a variable side, and in the other, like the complementary chance, it should be a invariable side. So today actually I go through all these 4 uncertainty measurement, which are base quality score, MapQ score, genotype likelihood, and the QUAL score. And these are base level, and MapQ score is read level. Genotype likelihood is individual level, and QUAL score is population level. And I should mention that apart from genotype likelihood, all these 3, like 1, 2, 4, measure the kind of like error measurement. So the larger this kind of flat scaled score is, the better the quality is. But for genotype likelihood, the flat scale score actually just describe the value of the likelihood. So the smaller the flat scaled likelihood score is, the more probable the corresponding genotype is. So this is an interesting observation, just to share with you guys. And I think that's the end of my presentation. Thank you.
Thank you, Lei. I think it was fantastic. So this is the second time I hear this, and it gets better and better every time. Next time I'll bring a popcorn and enjoy it even more. I think it's also, I think it's the first time that I have seen a thorough walkthrough of all levels of uncertainty that is that pertains to high throughput sequencing data. I think it's fantastic. We should videotape it and start selling it to YouTube. I think that's yeah, good. I of course don't have any questions. So I would also say that if this was a student project, or if this was a class teaching exercise, there would have been more exercises and stuff like that. That's what we had at the local course in Copenhagen. But I think the scope is also very, very big. I would say that it would even count as a seminar session at conferences if there's a background information. I think it's fantastic. Are there any questions for Lei here?
Yeah, sure. I have a question, not like question about the talk itself, but just a more general one. What is of the biggest importance as you think? Basically, we can make our data, like I'd say, better by making longer reads. We can make our data better, but making more reads, and we can make our data better by making reads more exact. Of course, all these 3 factors contribute for the exactness of our problem solving. But what is your personal opinion on which of the factors would benefit the most from its, let's say, maybe linear improvement, something like that? I'm sorry, the question is a bit too non-specific, but I just really wonder.
Yeah, I kind of think based on current technology, it is very hard, especially for the Asian DNA, you can extract maybe longer arrays or something like, but for the modern DNA, maybe you can do that by advance the technology. My understanding is maybe longer arrays is a better way, but currently actually longer arrays actually is the best way. The longer arrays actually cost a lot of money. That is my understanding. Tofin, do you agree with me?
Yes. So this would be tremendously useful because this would improve the mapping accuracy. And I think this is one thing that the current genotype likelihood models does not really take into account properly. So this, I would say that the state of the art within the current genotype likelihood models are relatively good. It's an ongoing project that we are actually collaborating with Vladimir on, but they are actually good. They can always improve them so they take into account more information. But it's really the mapping quality and trying to deal with these incorrect mappings. And that also has to do with the mapping technology. I talked about the linear mapping, where you're mapping to a representation, a haploid representation of your reference genome. There are other tools that are called variant graphs, which is also currently being used, that might do a better job. The issue here is, of course, that you might have reference biases. This is also something that Lea has spent a long time trying to model in a regression framework, and that is definitely an issue with the standard BVA alignments, with these linear mappers. So that's something, but it depends on the project itself, I would say. If you're looking into very, very fine-grained resolution within a very small population, say like the Danes, right? So the Danes are very homogeneous, and there's not that many of us, and we wanted to look at the migration patterns of Danes. Then because there's so little variability within the Danish population, I'm not talking about now, I'm talking about 200 years ago maybe, we have a lot more variation these days. So it's... you need to have very, very reliable inference methods. But if you're moving things into a global context, if you're looking at something between, say, the Chinese and Danes, for instance, right now I'm choosing China and Denmark because that's what we have here. Then it's going to be a lot easier, and then you don't need the same accuracy in the inference because there's so much information and signal in the data itself. It's the same thing that if you're doing a regular population genetics within a population, then there's some variability. If you move into a phylogenetic context and look at signals between species, then you have tremendous information. This is also some of the things that's being used in the selection scans, so that you can use this information to your advantage. I'm not sure if that answered the question.
Well, the question, I don't think that it has like the very specific 100% accurate answer. Like, yes, the length of the reads is the most important dot. So yeah, I see what you're saying. Okay, it's like very, very interesting. Thank you for the answers.
Yeah. And so it's also this thing, especially if it's with short reads. If it's with the short reads that you're working, then if they're only 30 base pairs long, then just by random chance it will map to multiple places in your genome. That's one thing, and it's also the organism that you are analyzing. Now we are talking a lot about humans, Danes, and Chinese, and maybe we should bring in some Russian examples the next time. So but if you're doing things for a non-model organism, like a new kind of salamander that lives in the middle of Africa, and you don't have a good reference panel, and you don't know anything a priori about this species, then it's going to be very, very difficult because your reference genome is very difficult to build. You can only do it from the few samples that you have, so you cannot build proper big size, proper chromosome, bound into contigs and scaffold. That will be one thing. And also what is used to an advantage for modern human stuff, and also ancient, is that you can do this thing of imputation, and you can do phasing. This is where the process of where you're using existing haplotypes that you know segregate in the population, and then based, so you know that there are some variants that are coupled. If you observe one, then with a very high chance, and you also know what the neighboring loci or position will be. So you can use this information to your advantage and then get much better genotype call than what you can do with standard genotype calling that is based solely on the genotype likelihoods. There's of course some recently developed tools for doing imputation and phasing using the genotype likelihoods, but still it's this requirement of having a good reference panel. And within human data sets, to my knowledge, the largest study that we have for full whole genome sequencing, not SNP chip data, right? There we have hundreds of thousands of individuals, but for whole genome sequencing in the context of NGS data, then I think it's 1,000 genomes that is the largest data set, and that's 2,500 genomes. So it's not a lot of information we have. Yeah. Good. Are there other questions for the? I understand it's a difficult topic, but it's very, very relevant, and I think it's very, very good. A lot of people that have worked with NGS data for a long time only have a very vague idea about what genotype likelihood is and what the actual quality score in a VCF file actually use, and it's used mainly just for cutoffs in their project, but it does contain valuable information. So I think it's very good. So if this course was given like a physical teaching course, then it would have, then the entire lay session here would have been a full day session, I think, with a lot of exercises in between and hands-on stuff about actually trying to run a BVA and maybe some other aligners. The same with the mapping part that I talked about. And this is when there's hands-on exercise, it also gives the possibility of actually making sure that all the information has seeped all the way down into the central part of the brain. Yeah, but this is a bit difficult with these online courses. Good. So I can also see that Lei was a lot better at keeping up with time than I am. Yeah. So thanks for that. It's 7:07 here in Copenhagen, so it's 8 something in Moscow. Yes. And Lei, thank you very much. I especially like that you had put the word Moscow in your header of your slides. I noticed that. Yeah.
Yeah, just
show
respect. Also, like I'd like to thank you guys. Actually, you are really hardworking. Like at 8 p.m. you are still working. Yeah, thank you.
Good.
Thank you very much, Lei. Thank you very much, Thorfinn. Yeah, the talks are really very exciting, brilliant. Yeah, thank you. And thank you, Thorfinn, for this session of all the 3 lectures. I think we really learned a lot. Yeah, I think we'll check it with some practical, like real scientific problems if people can apply all this information in the real world studies.
Yeah. So maybe next year there will be a possibility to actually do physical teaching in Russia next year, maybe. Huh?
Oh, that would be
just
so. Great. Right.
Yeah, so thank you again. Thank you, Thorfinn. Thank you, Lei. And yeah, we will have 2 lectures next week on Wednesday and on Thursday, one by Russ Corbett and another by Rasmus Nielsen. So see everyone in a week. Thank you again for our mentors, teachers, I don't know how to call you, lecturers. Right. Thanks everyone and have a nice evening. See you soon.
Bye.
Goodbye.